Hello. Welcome to Planning Your Solar System Road Trip. In my recent video on asteroid mining, I had to do some calculations about how much energy it took to get from the Earth to various asteroids. And that was something new to me, and I thought it might be new and interesting to other people. So I decided to do this video. I have a warning at the starting. The numbers in this presentation are for entertainment purposes only. Please consult a qualified trajectory professional before embarking on any trip outside of the Earth's atmosphere. I'm going to start by talking about road trips, normal kind of road trips. So let's say I wanted to drive from Seattle to Boston. It's about 3,000 miles. Let's also assume there aren't any gas stations. So, I own an Outback. It holds about 17 gallons of fuel. It gets about 25 miles per gallon on the freeway. That'll take me about 422 miles. So obviously, 422 miles is much less than 3,000 miles. So what could I do? Well, it can carry about 800 pounds of cargo. A 5-gallon gas can weighs about 43 pounds loaded. And I can carry 18 of them inside the car for 90 gallons of extra gas. This is pretty clearly a very bad idea. That gets me maybe 2,250 miles more of range, or maybe a little less, because I won't get 25 miles per gallon with that much weight. So what else could I do? Well, I could add a trailer to the car and put a bunch of gas on that. That might work. I could find a car that gets 50 miles per gallon and therefore needs much less fuel. Obviously, higher miles per gallon gets me a lot farther. Or I could try something different. Maybe I could put it on a truck, and that can take me part of the way, and then I can drive the rest of the way. So that's kind of how road trips work, and kind of keep that in mind during the rest of the talk. So if we want to take a road trip in the solar system, the first thing we need to do is get off of the Earth. And so here's a picture of the Earth. We're actually looking at the South Pole. So we have a rocket sticking up. And what I want to do is take that rocket from the surface of the Earth and put a payload into orbit. And obviously the rocket and payload are not to scale. So what does an orbit mean? Well, in this case, I'm going to choose an orbit that's about 200 kilometers off the Earth's surface. And we would call that low Earth orbit, kind of the low end of low Earth orbit. So I can go and do a little math based on the physics of orbits, and I will find out to be in that orbit, I need to be moving around the Earth at about 7,800 meters per second. So that's pretty darn fast. Orbital velocity is around 18,000 miles an hour or 25,000 kilometers per hour. So we're going to talk about how hard it is to get someplace based upon how much velocity we need. So using those same units, meters per second, it's going to take me a little energy to get from the Earth's surface up to 200 kilometers, and that ends up being only about 260 meters per second. So very interestingly, the getting into orbit, getting up is really easy. Getting sideways fast enough to stay into orbit is much, much, much harder. So it's kind of an interesting outcome. So we could look at this and say, what does it take to get into orbit? Add 7790 and 260 and get something a little over 8,000 meters per second. But that's not quite as easy as that. So it turns out there's some other forces we have to deal with. And the first one is drag. So you think if our rocket's going up through the atmosphere, it has to push the air out of the way, and that causes some drag. And to limit that drag, we will specifically choose a trajectory where we spend not that much time in the atmosphere. So rockets will spend a little bit time, mostly go straight up early in their trajectory and then turn sideways. That limits the amount of energy they lose to drag. On a typical trajectory, you lose maybe 160 meters per second to drag, so it's really not that much. There's another force acting on the rocket, and that's gravity. And you can think about this as, what would it take to just hover as a rocket? So the rocket takes off, goes up a little bit, and then just hovers. And obviously, to keep it from falling back to Earth, we need to be providing some energy, some thrust, pushing it up. So we're trying to oppose gravity. You might remember, or you might know, gravity is about 9.8 meters per second squared of acceleration. So if we are just hovering, we need to provide 9.8 meters per second to counteract the amount the gravity would pull us down. So that's how we'd hover. Now, it's a little more complex than that. On a launch, we start facing straight up. And so straight up, we just launch 9.8 meters per second, get farther in our trajectory, and it's 6.9. And finally, when we get into orbit, it's 0 meters per second. Gravity is still pulling at us, but we're going fast enough that the gravity will bend us into a circle, and that's what orbiting means. We're going fast enough that the gravity keeps us going around. So to figure out how much energy we actually use to counteract gravity, what we have to do is look at every second of the trajectory and how much of our thrust is going against gravity. And if you add that up for a typical trajectory, it might be around 1,600 meters per second. If you have a rocket that takes off particularly quickly, makes it to orbit earlier, it spends less time fighting gravity, so it loses less. And vice versa if you have a rocket that takes off very slowly. These losses, we have drag losses on the left, and then we have gravity losses on the right. And it turns out, looking at the size of the numbers, gravity losses are actually pretty important. So there's one more factor we need to take care of here. If we are launching to the east, the Earth is already rotating in the easterly direction. So we get a little bonus. We already have some velocity to start with. How much velocity depends on where we are. If we're on the equator, we get more velocity. If we were all the way at one of the poles, we'd get no help because the surface isn't actually moving. Around Florida, it's about 410 meters per second. So if we take all of these numbers together, add them up, and we get to about 9,400 meters per second. Now it might be a little lower, might be a little higher. That's kind of basically a ballpark. So now that we know what it takes to get off the Earth, let's look at a couple launch systems and kind of see how they rate compared to that 9,400 meters per second we're looking for. Oh, sorry, need to do something first. So that value is a change in velocity. We write it as the Greek letter delta, which is often used to mean change, and v, velocity. So delta v, or simply in English words, delta v. And delta v is simply the amount of velocity change that is necessary to move a spacecraft from one place to another. Where that place might be a planet, it might be a moon, it might be an asteroid, or it might just be some specific orbit that we want to get to. So by analogy with our road trip, delta v is the distance we need to go. And it's harder to go a longer delta v, a bigger delta v, than it is to go a longer distance when we're driving. So another concept we need to talk about, which is specific impulse. Usually written as ISP. And this is a measure of the rocket engine efficiency. It's a little bit like fuel economy in a car. If you have a car that has better fuel economy, you go farther on a gallon of gas. If you have a rocket that has a higher ISP, you get more thrust from a given amount of fuel. And ISP depends on a few things. Part of it depends upon the fuel that the rocket engine uses. And this is really all about the chemistry, the chemical reactions that are happening in the rocket. So the first three choices, LOX is liquid oxygen, and then our RP1, which is refined kerosene, LH2, liquid hydrogen, LCH4, liquid methane, and all of those have different ISPs. The first one has the lowest ISP. The second one with liquid hydrogen has the highest, and then liquid methane is kind of in the middle. The fourth fuel is a interesting fuel. This is what is called a hypergolic fuel, which means you have two components and they ignite on contact rather than you needing some sort of ignition circuit. And these are used a lot for space probes because they're relatively easy to deal with, and you don't need a lot of complexity. They do tend to be highly toxic, but that's something you can kind of deal with. The first one, MMH, is monomethylhydrazine, and the second one is nitrogen tetroxide. So fuel and oxidizer for that. The other thing that affects ISP is the design of the engine. Kind of to talk a little bit about engines, there are pressure-fed engines where you just have fuel, you pressurize the tank it's in, that pushes fuel in and that burns. There are gas generator engines where you have a small combustion chamber that drives a turbo, and then that drives a pump that pumps the propellants into the combustion chamber. And then finally there's an advanced one called stage combustion. And those are roughly in order of increasing specific impulse. So the best engines will have stage combustion engines. They will be the most efficient. Combustion pressure is really about how much fuel you are pushing in during a given time, and that can also increase your ISP. And then there's some other factors I'm not going to talk about here that will also have an effect on ISP. So just keep in mind, it's like fuel economy. So that takes us to something called an ideal rocket equation. Sorry, I flashed that. And this lets you relate some of these factors together. Now this is what you'll find on a NASA site. This is the derivation of the rocket equation. This is way more complicated than you need. So we're going to go look at a simplified version. And here's the simplified version. Okay, this may still look complicated. Basically, in this version, it will tell us how much velocity we can get for a rocket engine with a given ISP and a given proportion of fuel in our spacecraft. So ISP is specific impulse, G is just gravity. That shows up simply because of how ISP is derived. Ln is natural log. M total is the total class of the spacecraft, total mass of the spacecraft. So if you have it fully fueled, this is how much it weighs, and M empty is the empty mass of the spacecraft. So if you know all of these, you can say, hey, if I have a spacecraft that's 50% fuel and it has this kind of engine with this ISP, I would expect to get a specific amount of delta V out of it. Now, I actually like to use a revised or rearranged version of this that looks like this. And basically in this one, we use delta V, divide it by ISP times 9.8, and we use that as the exponent for E. So this is kind of the natural log backwards. And then that tells us something really interesting. It says, if we have a given ISP and we're looking for a given amount of delta V, how does that constrain the design of our spacecraft? And I don't really like M total and M empty. I like the amount of fuel or the percent fuel. So we just do a little rearranging here. M total minus M empty is the amount of fuel. So it's really the amount of fuel divided by the total weight with fuel times 100. So that would tell us, does our structure need to be 25% fuel? Does it need to be 50% fuel, or does it need to be 90% fuel to get a given amount of delta V? So once we have these equations, we can do some graphs. I actually did this one in Excel, and you can see there are 4 graphs for 4 different ISPs. And if we look to the left side, we see something, say we're looking for 100 meters per second of delta V. So go to 100 along the bottom, go up, and what do we find? Well, we find that, not surprisingly, higher ISPs require less fuel. It's not a surprise, it's kind of like fuel economy. But we find that in that range, no matter what our ISP is, we only need somewhere between 25% and 33% of our structure, of our total mass to be fuel. So that doesn't seem very hard. You know, we could have a probe that is mostly probe and only a fraction of it is fuel. And then as our delta V requirement increases, it goes up and up and up and up. And we notice if we get over to the part near 9,000, where we're thinking this is enough to get to orbit, it's actually pretty complicated. So, or pretty hard to do. Even at ISP equals 400, we still need about 90 or maybe a little over 90% of our structure has to be fuel. So that leaves us only 10% for all the structure and all the payload. So let's see how this applies to some real launch vehicles. You can see that's the region we're going to be looking at because we're trying to get to low Earth orbit. It's about how much delta V it takes. So I'm going to start with the Falcon 9 first stage. I thought that would be something people are familiar with. The numbers I'm going to present, you could either read from the graph I had on the last one, or you can go to this website here and it has a calculator that'll let you play a bunch of what-if games. So Falcon 9 first stage, the Merlin engine on it runs on RP1 and liquid oxygen. The sea level engine has an ISP of about 300, maybe a little more. For 9,400 meters per second of delta V, that means that our vehicle must be 96% fuel. We can go and grab some numbers. These are probably estimates, but they're relatively close. 25,000 kilograms dry weight, pretty close to 400,000 kilograms propellant weight. Falcon 9 first stage is about 94% fuel. And what does that tell us? Well, 94 is less than 96, so a Falcon 9 first stage cannot make it to orbit even with no payload at all. We could plug those numbers into the other equation, and we find that it only gives us a delta V about 8,300 meters per second. So that's not any good. What about a different stage? So this is the core stage from the SLS rocket. That will be used for Artemis, and this uses the RS-25 engine, used to be used in the space shuttle, and it has an ISP of about 400, so this is a considerably more efficient engine. We can go and look at our chart. A rocket with this engine only needs to be about 91% fuel to get into that orbit. So once again, run some numbers, and we find that for the SLS core stage, 91% of the weight is fuel. So that looks like, hey, the SLS core stage could barely make it into orbit. It wouldn't have any payload, but it could barely make it into orbit. But if we dig a little bit further, we find that 4 engines isn't actually enough to get this thing off the launch pad. We would need 7 engines to get it off the launch pad without the solid rocket boosters that it would normally have. So that bumps the dry weight up, and guess what? We're down to 89% of the weight as fuel. So SLS core can't really make it to orbit. And that brings us kind of to the broader talk. What about single stage to orbit? Even with some of the best engines we have, the Merlin for the Falcon 9 and the RS-25 for the SLS core stage, we can't get current rockets to orbit with the first state with a single stage. They simply weigh too much. We can't have enough of that being fuel. And that is without, neither of those rockets have wings or some way to get back, to control their path coming back. Neither of them have thermal protection against re-entry. And neither of them, we were talking about payload, that was just the rocket. So this is an indication of why single stage to orbit is so hard. It's simply very, very hard to generate enough delta V, given the kind of engines we have and the limitations we have with the efficiency. There's a possible caveat here. In the lower right, I'm showing a vehicle that is called Skylon, and this uses an engine that is designed to use oxygen from the atmosphere during the first part of its launch, and then switch over to oxygen inside for the later part. So that means when it's in the atmosphere, it's only burning fuel, and that, not surprisingly, pushes the ISP up much, much, much higher if you aren't carrying fuel. Whether this is enough to make it practical or even feasible, we do not know. The problems are still very significant to build this exact vehicle. So we'll see. Big rule, SSTO is very hard. So if we can't do it in a single stage, maybe we could do it in a second stage. Remembering back to my road trip analogy, I couldn't do it in my Outback, but what if I put my Outback on a flatbed and use that to get part way? So let's look at a stage we understand. This is the Falcon 9 second stage. Empty mass is about 4,500 kilograms. We know that for Starlink launches, which seem to be the heaviest launches it's done, the payload is about 15,600 kilograms and a propellant mass of about 115,000 kilograms. So that's 85% fuel. And that doesn't seem very good compared to the numbers we saw before, but remember that this is 85% fuel, including payload, not in a case where we're not carrying any payload. So this is the real world example for when this is actually launched. Go back, look at our graph or calculator, and we find that if we use the engine that's on the Falcon 9, its ISP is about 348. It's a little higher because it's a vacuum engine. We get a delta V of about 6,500 meters per second. So that's most of what it would take to get into orbit, but not quite enough. So what do we need? Well, we need the flatbed truck to get us part of the way. And that flatbed truck is the Falcon 9 first stage. And this is a screen grab from a recent Starlink launch. And so that gives us some stats right when the first stage was finished and the second stage was taking over. So what do we see? We see the speed is about 7,900 kilometers per hour. If we convert that, we get 2,200 meters per second. So add that to the 65, and what do we get? We get 8,700 meters per second, and that doesn't seem quite enough. But remember that we had other losses that we were trying to deal with. And those other losses were the drag loss. Well, at this point, we're above the atmosphere. So the first stage dealt with all of the drag loss. And it also turns out that the first stage dealt with much of the gravity loss. So we put those two together, and it turns out that the first stage can give the second stage just enough oomph that it can make it into the orbit that we want. And there's really an optimization problem here, deciding when you want to stage based upon the mass of the first stage and how much payload you're doing and all of that. Now, the interesting thing you probably noticed here is that most of the delta V came from the second stage. The first stage really didn't give it that much of the delta V. And this is a very deliberate choice by SpaceX. They very deliberately designed a big second stage that is very powerful, and a first stage that is comparatively not powerful. And the reason they decided to do that was they wanted to reuse the first stage, and the less delta V that the first stage provides, the less velocity it has and the less energy it has that it needs to get rid of when it comes back into the Earth and lands. So, for example, if you switched the ratios, if you looked at a rocket more like the Atlas V, most of the delta V comes from the first stage, and the second stage really doesn't provide quite as much. But that means the first stage, when it's done, it's going much, much, much faster. So it would be much harder to recover. So This is why we have two-stage rockets, and this is why different companies make different choices as to how much delta V they get from the first stage and how much they get from the second stage. So that's getting into low Earth orbit, time for a trip, and I'm old enough that when we'd go on car trips, we didn't have the internet. So we would get out a bunch of road maps, and all these road maps have little numbers, and that'll tell you how far it is on the road to go from one place to another. So you can just walk along the road map and figure out, from one point to another, add up all the numbers, and that tells you how much distance it is. And it turns out that there's actually an analog to that for the solar system. And this is, I don't know if you can read this, this says delta V map of the solar system. And I'll give you a link below where you can find it directly, or you can just search for delta V map of the solar system. So basically what this shows is a whole bunch of different bodies in the solar system and the delta V on the segments to get from one body to another. Now, it won't be perfectly accurate because sometimes going from A to C is cheaper than going from A to B and B to C, but it's roughly correct. And it'll give us at least answers that we can use to kind of play what-if games. So the first place seems logical to go is to go to the moon. So let's assume that we started in low orbit, and we need to figure out how much delta V does it take to get to the moon. So first step is to a spot called geostationary transfer orbit. It's about 2440. Moon transfer 680. Capture escape 140. Low orbit 680. That's in low moon orbit. And then finally down to the surface of the moon 1720 meters per second. So add that all up, and that's about 5660 meters per second. Okay, we can plug that into our calculator, and we would say that a 10,000 kilogram spacecraft only has a dry weight of about 1,500 kilograms, or about 15%. So that's going to be a significant challenge for us. And that's just getting to the moon, that's not getting back. So what can we do about this? Well, the first thing we notice is that some of our trip is trying to escape from the Earth. And we can do that with our launch stage. We can't slow down with the launch stage, or probably not easily, but we can speed up with the launch stage. So these first two segments, we're going to use our launcher. And for the Apollo missions, it was the third stage of the Saturn V. Pretty much got everybody else, all the remaining part, to the moon. So then we have the remaining part, and here we have about 2,540 meters per second left. And we can do that if we have 45% of 45% structure and 55% fuel. That seems a lot nicer than the other option. So that gets us to the moon. What about coming home? Well, coming home, we add things up in the opposite direction, and 1720, 680, 140, 680, and so on. And we get a total of 14,660 meters per second. And, okay, I just did the equation, and that would be 0.8% structure and payload, all the rest fuel. Okay, so that can't work. There's no way you could do that. But it turns out there's something else we can do. And this is indicated on the map I linked to, and here with these red arrows. And what that means is, if we're going in the red arrow direction, we can do aero braking. And if you know anything about Apollo, coming back from the moon, we had the command module, and it actually didn't really have engines. Maybe some small thrusters, but not engines. And that means that we can get rid of a bunch of energy by aero braking rather than using engines. And in coming back from the moon, aerobraking gives us about 12,000 meters per second. So the vast majority, that leaves us with the return only being about 2,500 meters per second. And realistically, you can't do anything in space from the Earth if you don't aerobrake coming back. It's just not practical. Trying to figure out how to get 9,000 meters per second from something already in orbit just isn't going to work. Okay, so we have this. We have a way of returning. And this is actually what NASA's original plan was. You would send out the spacecraft. Part of the spacecraft would land on the moon, and then it would come back all the way to the Earth. And to do that, NASA designed a rocket that they thought was big enough, and that's the rocket on the far right. That's the Nova. And you can see far left is the Saturn 1, typically known as the Saturn 1B. The center is the Saturn 5, what was actually used for Apollo. And then on the right, we have a rocket called the Nova. You can notice how much bigger it is than the Saturn 5, which is already a very, very big rocket. So basically, NASA figured they could do it with the Nova, but the Nova was going to be very, very expensive, and they didn't know if they could do it, afford to build it. So they came up with a different approach. And that is an approach called Lunar Orbit Rendezvous. And we can understand why they chose this approach if we look at the various vehicles that they used to do the moon missions. So we start out with a Saturn V, and that gets us into Earth orbit, and then we use the third stage, and that gets us out of low orbit, out of geostationary transfer orbit, and all the way to where we're going towards the moon. Okay, so you can think of 3 stages to get you that far. And then we have, many of you probably know this, we have the Command and Service Module, the CSM, and the Lunar Module together going to the moon. And we want to go and get into low orbit. And what if you do, if you look at the delta V numbers, you notice we have 140 and 680, that's 920. So it's really not that much delta V to get into low orbit. And what does that mean? Well, that means the Command and Service Module doesn't have to be a high proportion of fuel, which is good because it has its own mass and it has the mass of the Lunar Module. So now we get into low orbit and we kind of have a problem. The Command and Service Module is too heavy to get down to the moon and back because there's a lot of delta V there. Just getting to the lunar surface takes 1,720 meters per second. That's a lot of delta V. So what do? Well, we don't take the Command and Service Module with us. We take just the Lunar Module. And it turns out, if you look, the Lunar Module on descent is about 54% fuel. That gives the Lunar Module about 2,500 meters per second of delta V. So that's enough. That's more than 1720. That's enough to come in and land. One of the reasons it's considerably more than 1720 is that they want some margin, which Apollo 11 and some of the other missions actually needed, so they could change their flight path. Part of it is they are not coming in at the most fuel efficient trajectory, which would be a very, very fast one coming down and a lot of thrust at the end. So their trajectory takes a little longer and the gravity losses are therefore higher. So let's see, on the Saturn V we had 3 stages. You can kind of count the LEM and CSM together as the 4th stage. So now we're on the 5th stage. And we're going to land that on the moon, and then when we come back from the moon, we want to, we also need to get 1,720 meters per second. But we're going to go to yet another stage, the 6th stage. And the LEM kind of breaks in 2. We use the top part of the LEM only, which is much lighter than the whole LEM. It's about 50% fuel. That gives us 2,000 meters per second delta V, enough to get off the lunar surface and enough to be able to maneuver and meet up with the Command and Service Module. So this is a really interesting technique. Lunar orbit rendezvous let us make the requirements of fuel for the command service module much lower, and then therefore made it possible to use a Saturn V rather than a Nova class. And then the LAM Ascent module comes back, and we're back with just the command and service module at this point. So we don't have to deal with the mass in the LAM, either the descent or the ascent stages. So we can use that, and now we need a relatively small amount of delta V just to get the command and service module back going towards the Earth. And then finally we have the command module left, and we can use aerobraking to bring it all the way back. And if you add up some of the masses, you find that the launch weight of an Apollo Saturn was about 2.8 million kilograms, and the return weight of the command module was about 5,900. So the final fraction is about 0.2% of the initial launch weight. And the fact that this was possible at all with the Saturn V is because of this particular approach where you use lots of stages and then you leave stuff behind so that you don't have to waste delta V and fuel getting it back. So that's the moon. Here's an interesting diagram I pulled from NASA. This shows the delta V. Here it's in feet per second, so you'd have to convert it to meters per second to make the numbers make sense. But what we can see, you can see translunar injection on the left. Oh, there's a lot of delta V there. That comes from the third stage. And then lunar orbit assertion and trans-Earth injection are the two burns done by the command and service module. And then we can see lunar module descent and lunar module ascent. And we can see those two delta V's are about the same. The descent is a little more because, as I said, we have higher gravity losses. And then finally, you look far right in entry and landing. None of that uses any delta V because we're doing aerobraking. So that was the moon. What about going to Mars? And here's a diagram going to Mars. It's a lot more complex. If we start adding up from low Earth orbit to get to the surface of Mars, we add up all the numbers and we get 9,510 meters per second. And that's a really big number. Just to compare it from low Earth orbit to the moon was 5,660. And that number for Mars is actually pretty big, but it's not as big as you'd expect it. We have this, I at least had this feeling that the moon was relatively close, but Mars is really not that much farther in terms of delta V. And in fact, if we look at this portion on the right, what do we notice? Well, we notice, like coming down and landing on Earth, we can come down and land on Mars using aerobraking. And we don't have any oceans to splash down into, so we probably need to reserve some amount of fuel to do a soft landing on Mars. But if we look at this, from low Earth orbit to Mars, if we do aerobraking, it's only 3,600 meters per second. And that intuitively makes no sense at all. It's actually easier if you build a probe that aerobrakes. It's easier from a delta V perspective to get to Mars than it is to get the surface of the moon. Totally surprising outcome. And of course, assuming you have a spacecraft that can aerobrake, and you have to have structure for aerobraking, and you still have to have engines to land. So your structure is probably heavier, but that's a significant difference in delta V. Going the other way, from Mars to the surface of Earth is about 5,700 meters per second. And that's including aerobraking to get back to the surface of the Earth. So the moon return is about 2,540 meters per second. So if you're looking round trip, it's a little harder. I think if I added those up, it's about 8,000 meters per second versus about 9,000 meters per second. 8,000 for the moon, 9,000 round trip for Mars. But surprisingly, not that much different. Now, of course, the travel time to Mars is much longer. Typically a couple months, and the travel time to the moon, is only a few days. And that matters a lot if you're going to send people. Not as much if you're going to send probes. So, other destinations. So, starting off in low Earth orbit, I just pulled some. You could go look at the map and look yourself. You can get to Europa on Jupiter and land. If you aerobrake at Jupiter, it will take about 14,000 meters per second. This is going to be difficult, even if you use your launcher to give you most of that energy. Conversely, you can land on Titan, on Saturn, for only about 7,300 meters per second. You can aerobrake at Saturn, and you can aerobrake at Titan. So this is another very surprising thing. Getting to Titan is much, much easier than getting to Europa if you want to land. Venus, going back towards the inner solar system, about 3,490 meters per second with aerobraking. Mercury, there's no atmosphere, so you can't aerobrake. If you wanted to land on the surface of Mercury, 15,000 plus meters per second. The asteroids, since we talked about asteroid mining before, the near-Earth ones are the easiest ones to get to, are about 3,700 meters per second. To get to, the main belt asteroids are about 6,800 or more. So they're actually pretty hard to get to. Harder to get to than Mars, certainly. The sun, people always ask, it's like we should send waste into the sun. If you wanted to just take something from Earth, you get it in Earth orbit, and you want to drop it into the sun, you have to cancel the Earth's orbital velocity out. That is about 21,000 meters per second. So it's a high delta V. If you wanted to go into solar orbit, 199,000 meters per second. And finally, if you wanted to land on the Earth, on the sun's surface, if that actually meant something, 639,000 meters per second. So those are some really big numbers. Even like getting to Mercury is a really big number. So are there any ways to cheat? Because these are all about generating delta V from fuel, which is what we've talked about so far. Are there ways to do it without fuel? And there is kind of this interesting way, and it's called gravity assist. So gravity assist can be used to speed up spacecraft by coming in behind the planet and exiting in the direction of the planet's orbit or the planet's movement. And I stole this little diagram from Wikipedia. And start by looking at the bottom planet frame. So what we can see is that our spacecraft is coming in towards the planet, and then it's kind of hooking 90 degrees due to the gravity of the planet, and then it's going away. And our intuition would kind of say that, as we're going towards the planet, we'll speed up, and as we go away from the planet, we will slow down. And that those will be the same, and that turns out to be correct if we are looking at what happens using the planet frame. However, when we're going around the solar system, we don't care about the planet frame. We care about the sun frame, how much velocity we have in relation to the sun. So if we look at the upper one, what really happens is we are taking velocity that's going sideways towards the planet and then converting it to velocity that's going forward away from the planet. But we are actually, the speed at which we're going away from the planet is above the planetary orbit speed. So essentially, what we can do is steal some of the planet's momentum to use us to push us forward. Or we can actually use it the opposite way. If we come at the front of the planet and exit behind, we can use it to slow down. So The caveat on this is it requires very specific trajectories. You have to get your spacecraft near enough a planet that you can use this effect, and that may be very inconvenient. Now, one usage of this was with the Voyager spacecraft, which were launched in the late 70s. And they were launched in the late 70s because the planetary alignment was convenient for actually doing this. So if you look at the red line starting way over on the left, in August of 1977, Voyager 2 was launched at about 35,000 kilometers per second. So that's very, very fast for a launch. And we can see as time goes by, as it gets farther from the sun, it slows down. And by the time it got to Jupiter, it's all the way down to 10 kilometers per second. So it slowed down quite a bit. But then there's that huge spike. That is the gravity assist from Jupiter. And then slows down again. We get a huge spike, gravity assist from Saturn. And then finally we get a small spike assist from Uranus. I presume that's because it wasn't in quite as convenient of a position. And then finally another big spike from Neptune. So that allowed us to take a probe that couldn't even have made it out of the solar system and achieve solar system escape velocity using these gravity assists. I came across another one really interestingly. The Parker Solar Probe is trying to get into a orbit around the sun that's kind of close, much inside Mercury at the closest point, the perihelion, and kind of around Venus's orbit. So it will be using the gravity assist approach to slow down. And it's going to have 77 gravity assist encounters with Venus. So you remember how hard I said it was to get into close solar orbits or Mercury orbits? This is a way that you can do it without using a ton of fuel. So they're just doing gravity assist over and over and over and over and over and over, and then they finally get there. The downside of this for this kind of gravity assist is it takes a long time. You can think going in these orbits is going to take months and months. So it's not like just flying a probe just there. It takes a long time. So another topic related to delta V. So as I said in Apollo, the conventional approaches create outward delta V using the launcher. So use that for Apollo, use that for Mars missions. Most typical missions, in fact, all the missions I know of so far use that. And that means you're limited. So talking about going to Mars, if we used a Falcon 9, we can get 4,000 kilograms going towards Mars. A Falcon Heavy, 16. Delta IV Heavy, only about 8. An SLS Block 1 is probably on the order of 30,000 kilograms. So 30 metric tons. But all of these are quite limited because we have to use a bunch of delta V to get to Mars, which means we can't use that just to lift a lot of weight into orbit. So orbital refueling. If we can look at Starship, and these are speculative numbers, even more speculative than the other ones, because we really don't know what Starship's going to end up with. But if you put a Starship into orbit and then you refuel it fully, a Starship with 100 tons of cargo has about 6,500 meters per second. You push it up to 200 tons of cargo, it's about 5,400 meters per second. Remember, Mars only takes about 3,600 meters per second from low Earth orbit. So basically, anything Starship can lift to low Earth orbit can be taken to the Martian surface, assuming you're refueled. Coming back, return from Mars, we looked at this before, it takes about 5,700 meters per second, plus you're going to need a little bit left to do propulsive landing. So what does that mean about cargo return? Well, you couldn't return 200. You might be able to return 100, but you're probably talking maybe 50 tons of cargo or payload coming back. on a return trip from Mars. So you're probably limited to that. One more final topic, and this is about getting to geosynchronous orbit. And this is a very interesting topic, and I don't think it's well understood. So geosynchronous orbit, this is like our trip to the moon, 9,000 to get to low orbit, 2110 to get to geostationary transfer orbit, and then 1800 to get to geosynchronous orbit. And geostationary transfer isn't really a specific orbit, it's a set of orbits. And they are described using the amount of delta V you need to use to get all the way to geosynchronous. So you'd say essentially it's a geosynchronous geostationary transfer orbit, and I'm missing a specific amount to get to geosync. So a lot of times capacities or payloads are quoted using GTO minus 100. So I can use my launcher, get you to GTO minus 1800. You'll need to put out 1800 to get to geosync orbit on your own. And there are others. There might be GTO minus 2100. There might be GTO minus 1400. It all depends upon the capability of your launcher and what you're willing to pay for to kind of make trade-offs here. Now, let's look at a specific launch system. So I picked Atlas V 551, which is they're big and beefy. It has 5 solid rockets on it, and it can do 3,960 kilograms direct to geosynchronous orbit. So can we do better? Well, it can do about 8,700 kilograms to geostationary transfer to a GTO minus 1800 orbit. So if we had it do that, what would it take to get to geosynchronous orbit? Well, it turns out we have that 1800 meters a second. If we look at the hypergolic propellants I talked about, which were typically used in a lot of satellites, we could get 4,828 kilograms to geosynchronous orbit. That's about 20 or 25% more than if we went there directly. And the reason that's true is we aren't taking the full second stage to geosynchronous orbit. We're just taking it part of the way. So this is the satellite acting as a third stage. And that's why it's a little better. The hypergolic propellants aren't quite as good as the second stage in Atlas. So that's why it's not more. But there's another option. We now have ion thrusters. And ion thrusters use a single propellant, typically xenon or krypton, a noble gas. And they use electricity to essentially get thrust. So we're using electricity to generate very high speed thrust, and because it's very high speed, it's very fuel efficient. So we get ISPs at 2,500 or even more than 2,500. So what does that mean? Well, we remember that ISP is an analog of fuel economy. So we would expect that it would take much less fuel to get from GTO minus 1800 to geosync if we use ion thrusters. And it turns out the difference is really substantial. So we can get over 8,000 kilograms to geosync using ion thrusters. So this is a reason that most communication satellites that go to geosync use ion thrusters now. Now, there are some downsides to ion thrusters. The first is you need a lot of electrical power because they're essentially using electricity to accelerate the fuel. And geosync communication satellites generally have pretty big solar arrays, so they can get quite a bit of power. So that's not that much of a problem. There is another problem. The engines we'd use for hypergolic propellants might take us about 5 hours. They aren't particularly high thrust. About 5 hours to get from GTO minus 1800 to geosync. Ion thrusters are much, much lower in thrust. So it might take 150 days to get there. So that means if you're using the ion thruster approach, you now have to wait like 5 months before you can start using your satellite and start charging people for communications. So there is a trade-off here, but the fact that it's so much more efficient means you have a couple options. You can carry more fuel so that your satellite can last longer, or you can choose a cheaper launch vehicle. Maybe you don't need the Atlas 551 variant, you could use a different variant. So that's another example of using staging to spread delta V requirements across multiple stages rather than trying to do it all at once. And that's all for the talk. I hope you enjoyed it. Thank you.